All right, so welcome to class. It is Friday, April 3rd, and today we are talking about momentum. Um, Reminders. Um, I'll send out an email a little bit later today about this too, but um, the completion rates on the Wiley Plus and Perusal since the coronavirus disruption happened have gone way down. And I'm getting concerned that either people don't know what's expected of them or what. I don't know. Maybe we're all just overwhelmed with things. But just as a reminder, as of today, you should have completed the chapter 7 and 8 homeworks on Wiley Plus and the adaptive practice for chapter 8. I've extended those deadlines, as I said I would. We'll keep pushing them back. But as this piles up, it sort of snowballs. So don't let yourself get wiped out by this. This can very easily run away from us. You should also have completed the video experiments number 1 and 2. Number 3 will be posted today. I said that last time, but I decided to cancel what was going to be number 3 because again, I haven't gotten very many of those submitted, and I'm worried that we're falling behind. I'll say a word about those here in a minute, and then just as a reminder, the Perusal reading was due today for chapter 9. Well, for the first part of chapter 9 on momentum. We'll have more Perusal reading due on Wednesday for the rest of chapter 9 that talks about collisions. So the Perusal reading is the only thing that I'm not pushing deadlines back on, because that really is preparatory to what we're going to do in class. So yes, so the homework, the Wiley Plus is, I believe, technically due at the end of the day Friday. The Perusal is due Friday at 6 a.m. Well, the day of its due date at 6 a.m. So functionally it's due the night before. But if you want to stay up late and do it at 2 in the morning, I guess you can. And with the Wiley Plus, it's not like if you haven't done it at this point, you've missed it. I am pushing the due dates back every time they're due. I thought I could make it have due dates, but still accept late work. Apparently, that's not an option on Wiley Plus, at least not an option I've figured out how to do. So what those are going to do is they'll, every time, I'm going to leave the due dates on because I want you guys to see them as I should have it done by this date. But then once we hit that date, I will move it back a week. So we're just going to step everything back a week, each time. Okay. Any questions about the Wiley Plus or the Perusal? Okay. Let me just really quickly talk about the video experiments. So I'm going to come over here and talk briefly about video experiment number 1, which was the cart with the spring on a slanted track. Because I think we're having a hard time understanding what it is I want you to do on these experiments. So for this experiment, there were 2 questions I wanted you to answer. One is, what's the spring constant for this cart, for that spring, right? And I showed how that was done, and the ones that have been submitted so far have done a great job with that. The second part was verify that the work energy theorem is holding here for the cart going between its highest point on the ramp and its lowest point on the ramp, okay? So the work kinetic energy theorem, so this is what I'd like you to have, something to this effect. Let me make it a little bit bigger. okay, a write-up something like this that says the work kinetic energy theorem states that the work is equal to the change in kinetic energy, right? Final kinetic energy minus initial kinetic energy. At the top and bottom of the track, the cart's velocity is 0. So that gives us the work has to be equal to 0 because both the final and initial kinetic energies are 0, okay? And then we could say there are two forces doing work here, the spring and gravity, so they must be equal, right? In different directions, one's doing positive work, one's doing negative work, but they must add up to the same thing if this work kinetic energy theorem holds. So we need to figure out how much work was done by the spring and how much work was done by gravity. To get the work done by the spring, we can integrate the force over the distance, which I have here. Just integrated the thing, and I got an area of 0.421 Newton meters. Or in other words, the work done by the spring is 0.421 joules. To get the work done by gravity, we can recognize that the force is constant. The gravitational force is constant. So the work done by gravity is just the force of gravity times the distance, right? The distance we can get from the data. We just take the minimum position and subtract it from the maximum position, which gives us a distance of 0.41 meters. The component of gravity in the direction of motion is mass times 9.8 times the sine of the angle. And if you put all that together, oh, I forgot a unit. You get that the work done by gravity is 0.449 joules. And if we compare the two, they're within about 5% of each other, which is pretty good, right? Pretty good. We'll take 5% difference here. So we can conclude that, yeah, these are consistent with the work kinetic energy theorem. Does that make sense? Yeah.
So you had force and distance or force and position.
Yes. So we had the force done by the force from the spring was measured by the sensor, right? Because the spring was attached to the sensor. So to get the force as a function of distance for the spring, we could just use the data, right? We could just take an integral of the force over the distance that the thing went from. The top of the cart is actually, the top of the ramp is actually the smallest distance, right? And the bottom of the ramp is actually the longest distance, right? So we could integrate how much force was being applied to the cart as it bounced, as it did one complete lap, right? And by taking that integral, we got the work done by the spring. Okay. Does that answer your question?
Yeah.
Okay. So really the thing that I wanted you to realize here is that if we took the work kinetic energy theorem, looked at the top and bottom of the track where the velocity is 0, right? Which gives us the total work being done between the top and bottom of the cart's motion is 0, which means that since there were two forces doing work, they have to cancel each other out. And if you actually look at this, gravity in this case, because we're going from the top of the track to the bottom of the track, right? The gravity is doing positive work here and the spring is doing negative work. That's not particularly important for our purposes. We just want to see that they're the same size. But you could figure that out as well. Okay, so that's the kind of thing I'm looking for that first one. And you can still go back and change the first one that you did however you need to, okay? For each of these labs, or video experiments, there's going to be at least one, sometimes two or more questions that I want you to answer. That I want you to go in, use the data, use what you know about physics, right? And make a prediction In this case, our prediction was that the work done by gravity should be the same but opposite sign as the work done by the spring. And then actually go into the data and compute those, right? Compute what we think the work done by gravity should be, or what the work done by gravity was, what the work done by the spring was, and compare the numbers and see if they were equal or not. Okay. So is that a little clearer?
Yeah.
Okay. So have a go at that. Look at what you turned in for the second video experiment as well, and see if and make sure that that's all working the way you want. And then I think probably starting next week, I'm going to turn the grading loose on those things, and we'll actually start giving you grades for them. Okay, let's go back to what we're talking about today. Okay, so what we're talking about today is momentum. And to start us off, we've got our little polling question that I can launch here. So you have a bowling ball and a baseball, and they've got equal velocities. Which one has more momentum? I'll give you another 10 seconds. All right, going once, going twice, sold. All right, everybody said it was the bowling ball. Everybody's right. Okay, so now here's the follow-up question to that. You've got a lead ball with a radius of 1 centimeter and a mass of 11 grams. A styrofoam ball has the same mass and a radius of 4 meters. They are both moving at the same velocity. Which has more momentum? Let me relaunch the poll here. There we go. All right, I'll give you another 10 seconds. Going once, twice. All right, sold. Okay, this is a mean question. What's the right answer?
Same.
Yes, they have the same momentum. They have exactly the same momentum because momentum only cares about mass and velocity. It doesn't care about the size of the object. So a 4 meter radius ball of styrofoam, right? So that's a ball that wouldn't fit in your room. Not even close to it'd be 8 meters tall, right? As tall as a house. would have the same momentum as a 1 centimeter radius lead ball. But the point is their masses are the same, and that's what matters for momentum. So when we talk about momentum, let me come over here to my dear friend, the document camera. Okay, so when we talk about momentum, momentum is fundamentally this concept that the momentum of an object is just its mass times its velocity. Okay. Oh, come on, camera focus. There we go. So momentum is just mass times velocity, right? And it's a vector. So momentum has direction to it. You can have momentum up, down, left, right, right? Momentum has direction. And that direction comes entirely from the velocity. The direction is just determined by the direction of motion. The mass is just scaling it, right? So if we go back to the baseball and the bowling ball, right, their momenta would be in the same direction, but would have different magnitudes. So if here's my baseball, right, which has some little amount of mass, its velocity vector would look like this, right? And its momentum vector might be different units, but we could draw it the same length, okay? Now we come down here to the bowling ball, right? There's a bowling ball. Its velocity vector is the same, right? We said it was the same. But its momentum vector is much bigger because the momentum gets scaled by the mass, right? So really what we're talking about here, this quantity called momentum, is not something we directly measure almost ever. It's a combination of two things we can measure, the mass of an object and its velocity. So momentum is sort of this, it's sort of a difficult concept. We use the term momentum all the time. It gets used in sports, right? The team, you know, the Patriots have all sorts of momentum on this drive, right? Whatever the terminology is, whatever that means, momentum, right? It gets used a lot. Momentum in physics, it has a very specific meaning. It's just your mass times your velocity. And it turns out momentum is a very fundamental concept. Turns out it's much more fundamental than just velocity. And here's why. So the word momentum is Latin. It's the word motion turned into a noun. So the or movement or move turned into a noun. It's momentum is what Newton called the quality of motion. That's how he translated the word momentum, the Latin version of the word, into English. The quality of motion. Momentum tells you how much motion an object has. And the motion of the object has two parts, both the mass and the velocity. Okay, why does this matter? Well, this matters because it turns out that momentum is fundamentally more important of a concept than velocity. So we remember Newton's second law, right? We write Newton's second law as the sum of the forces equals mass times acceleration, okay? Well, we can rewrite acceleration as the derivative of velocity with respect to time. But this isn't the way Newton wrote his second law. The way Newton wrote his second law was simply that the sum of the forces on an object is equal to the time rate of change of the object's momentum. And you can see that these are right. If I take this definition and I plug it in here, I get that this is the time derivative of mass times velocity. And if I assume the mass is constant, this is mass times acceleration. Okay? But it turns out this definition, this one right here, is more general than this one. Because we had to make an assumption here. We had to assume the mass was constant. Now, masses of objects usually don't change very much when they're moving, but some of them do. For example, a rocket. In a rocket engine, the mass of the rocket is changing because it's burning fuel. This definition works for a rocket. This one does not, because the mass is changing. Okay? So this is what I call Newton's version of his second law, that the sum of the forces on an object is equal to the change in the object's momentum. Interestingly enough, it turns out this version even works for objects moving close to the speed of light. This definition still works. This one doesn't. So this is really the fundamental thing, that when you have two objects interacting, right, forces are interactions, what that causes is a change in the momentum of the object. So let's do an example. Let's imagine I've got my object here and I apply some force to it, okay? I'm going to apply a force, okay? And I'm going to apply, and I'm going to make that force whatever, right? It could be due to somebody pushing it. It could be due to friction. It could be due to, something crashing into it, a rocket engine, whatever, right? That force applied to the object is going to change its momentum. So what that means here is that if I wrote out Newton's version of his second law, that force is going to cause a change in my momentum, which means that my momentum, the change in my momentum is going to be equal to the integral of my force over time. Okay, now this is interesting. This would look like something. What does this look like? This idea that my change in momentum is equal to an integral of force over time.
That's equal to impulse.
Well, it is equal to impulse, right? That's what we call this term here. This term right here, we're going to call impulse, which is usually written as capital J. But this form, that the change in something is equal to an integral of force over something, what does that look like? What does that have the form of?
Does it work?
It does look a lot like work, right? The work kinetic energy theorem says that the change in kinetic energy is equal to the integral, the work, right? Which is the integral of force over distance. Okay? So all this is this, it's the same form, but it's a different result, because now we're integrating in time rather than integrating in space. And what we get out is the change in momentum as opposed to the change in kinetic energy. But it has the same form to it, right? It looks the same way. Mathematically, they have the same shape, right? The same kinds of relationships. Okay, so let's do an example of this. If I come over here and switch my screen and hit share, there we go. All right, let me relaunch the polling question. There we go. Can you guys see the poll? I will take the stunned silence as a yes. All right, wave at me if you can't see the poll. Nobody's screaming, so I'm going to count that as good. All right. So what we've got here is a situation where you've got Frank. Frank hits a golf ball with a mass of 45 grams with a baseball bat. Then Frank hits a baseball with a mass of 145 grams. If Frank hits both balls with the same force and both balls are in contact with the bat for the same amount of time, which ball has more momentum? All right, I'll give you another 15 seconds. All right, going once, going twice. All right, sold. Okay, so we had a nice spread there. Let me share the results with you. C was the most popular. We had some people who liked B, and we had one person each that wanted A and D. All right, who wants to defend A? One person said it. You want to admit to it? All right, nobody wants to admit to A. Okay, B. Somebody want to defend B? Oh, come on. There were 4 of you that said B. Somebody had to think that.
I didn't have enough time. I kind of just picked B.
All right, desperation shot. Anybody else want to defend B?
I said A, but I'm
Oh,
looking
there
at
you
it
go.
now and I'd probably go for B because the masses on the baseball is bigger. And then looking at the equation, it would make the momentum higher for the baseball.
Okay. So the baseball has more mass, right? So if they had the same velocity, the baseball would have more momentum. Okay, I can buy that. All right, C. Who wants to defend C?
So the golf ball will have more velocity, but because the formula is just mass times velocity, the velocity that the baseball doesn't have will be made up through its mass, so they'll have the same momentum.
Okay, so you're saying that the way this will work, the baseball will be going slower than the golf ball. How do you know that?
Because it has more mass, and so if you apply an equal force, it's going to be going slower.
So you're saying if you apply equal force, it will accelerate less, right? Or if we go back to this definition that involves momentum, right? An equal force will cause the same change in momentum. Okay. Anybody want to defend D? Okay, so I'll give you a little bit of backstory on this question. It turns out this question, one of the early times I taught this class, this was actually a test question. And I actually got in trouble because it turns out that the correct answer here is actually D. Because And I'll walk you through why. I meant it to be C, but the correct answer here is actually D. Here's why. Okay, if we go back over, let me go over here. Okay, if we come over here to our setup, right? What we know is that when both balls get hit, right? There's the baseball, there's the golf ball. They both get the same amount of force, right? And the forces last for the same amount of time, right? So the time is the same. Which means if I go back to that definition of Newton's second law, right? My force is equal to my change in momentum with respect to time. And if I take that apart, right? If I move the dt over here and I integrate both sides, what I get is that the change in my momentum is equal to the integral of that force over time. Now, the forces are the same, the time's the same, which means that for both balls, this is going to be the same, right? Which means that the change in momenta for the two balls are going to be equal. But here's why D is actually the right answer. I didn't actually tell you what the motion of the balls were before they were hit. So to actually answer which one has more momentum after the collision, after being hit by the bat, we'd have to know what they were doing beforehand, because the change in momentum is what matters, right? That momentum gets changed by force over time, or by a force applied over a time interval, right? So D is technically the right answer. But I actually, when I wrote this question, I meant it to be C, right? That both balls would have the same change in momentum. So here's the crazy thing, right? And it's exactly what I think Davey was saying, is that the force accelerates the big ball less than the little one, right? The baseball gets a smaller acceleration. And those two things work out exactly to cancel each other. So that what ends up changing here is just the momentum, and it changes in exactly the same way. As long the momentum changes the same way, as long as these two forces are equal and that they're applied for the same amount of time. Okay, now here's the follow-up question to that one. Let me go back to sharing my screen. Okay, follow-up question. Same scenario, but now I want to know which one has more kinetic energy. Let me relaunch the poll. There we go. Okay. So which ball now has more kinetic energy?
Did you launch the poll?
I did. If you've closed it, you can get it back down at the bottom of your screen.
There's not an option for that. I don't see it.
Yeah, it's not visible.
Okay, well, let me try closing it down and relaunching it.
There
How
you
about
go.
that?
Oh,
Did it come
I
back?
see it now. Yep.
All right. Seems to be a little finicky. Usually when I relaunch the poll, it pops up for everybody, but sometimes it doesn't.
Do you still want us to assume we're clueless about their momentum and like velocity before they get hit?
No, you can use what we just learned, right? We just learned that they have the same momentum. Oh, by the way, I'm going to say that they have the same momentum afterwards because they both were starting at rest or something. All right, I'll give you another 10 seconds here. All right, going once, going twice. Sold. Okay, so let me share the results here. All right, nobody went with more information to tell. Good. Okay, but we had a nice distribution. So what I want you to do here, I want you to come up with an argument for your point of view. Okay, and so let's start off with the golf ball. Who wants to argue for the golf ball?
I will argue for the golf ball.
Go for it.
So-
Defend that golf ball.
Both are hit with the same amount of force and time, so the golf ball will be going much faster than the baseball, and velocity is squared in the kinetic energy equation, so that matters more than the mass. So that's why I say the golf ball.
Okay.
That's why I said that too.
Okay, we got two people willing to defend the golf ball. All right, baseball folks, tell us why the baseball has more kinetic energy. Oh, come on, baseball folks, where are you on this one? There are 5 of you.
Okay, I chose the baseball, but then looking back at the equation, I think I would switch it to the golf ball.
Aha.
And the reason being is because velocity would equal momentum over mass. So that would mean that the mass is on the denominator. So if the mass is greater, that means that the velocity would be getting smaller. So if you have a smaller mass, that means that the velocity is greater. And it's 1/2 mass times velocity squared. So
Okay. You were very convincing, Lucas. Okay, so it turns out that he's absolutely right, that the golf ball has more kinetic energy. Okay, here's how you can look at this. And you're exactly right to say that if the momenta are the same, right? So let's say here's our momenta of the golf ball and our momentum of the baseball, right? That means the mass of the baseball times the velocity of the baseball is equal to the mass of the, wait, I've switched sides here. Golf ball, mass of the baseball, velocity of the baseball. Okay. So that because, what was
Can
that?
you make your paper bigger?
I cannot make the paper bigger, but I can write bigger.
No, what I'm trying to say is we're still on the screen with the question.
Oh, okay. I can stop that. There we go. That go away?
No.
Not
The question didn't go away? Oh, I know what you're saying. Aha. There we go. This is what you mean, right?
Yep, perfect. Thank you.
All right. Okay, let me try that again. So the momentum of the golf ball is equal to the momentum of the baseball. That means the mass of the golf ball times the velocity of the golf ball equals the mass of the baseball times the velocity of the baseball. Okay? So because the mass of the golf ball is small, the velocity of the golf ball is big. Okay? Compared to the velocity of the baseball. In other words, if I rearrange this, right, if I put all the masses on one side and all the velocities on the other, the mass of the golf ball divided by the mass of the baseball equals the velocity of the baseball divided by the velocity of the golf ball. Okay? So this is a small number divided by a big number. So this has got to be a small number divided by a big number. They have to go in proportion to each other. Another way to think of this is we usually write kinetic energy as 1/2 mv squared, right? And our definition of momentum has velocity in it. So we could solve this thing we could solve that for velocity. So momentum is mass times velocity, which means that velocity is just momentum over mass. if I take these two equations and put them together, I get that kinetic energy is just your momentum squared divided by twice your mass. So because the objects have the same momenta, but different masses, the lighter object has more momentum. This is why you don't want to get shot by a bullet, but you don't really mind if you get hit by a baseball, okay? A hard thrown baseball and a bullet have roughly the same momentum. One of them will give you potentially a bruise. The other one could kill you. And the difference is not their momenta. The momentum of those two is fairly close to each other. The difference is their kinetic energy, right? Because that little teeny bullet has a small mass, and so it has a huge velocity. And that velocity gets squared, which means it's got a lot of energy, which means it can do a lot of work on you, right? Because that's what kinetic energy can do. If you want to stop a bullet, you're going to have to do a lot of work on something. And generally speaking, you don't want to do a lot of work on yourself, right? Particularly your insides. Okay, so momentum is this tricky concept because it's not kinetic energy, it's not velocity, it's not mass, it's something related to all these things. But it turns out that the universe likes momentum a lot, okay? And as we'll show next time, it turns out that Newton's third law is actually a statement about momentum, okay? I taught it to you as a statement about velocities, but it's really actually a statement about momentum. We'll get to that one next time. Okay, so here's what I want to do. I want to come back over here, and we're going to talk about car wrecks. Okay, it turns out that one of the, actually, let me go back a slide here, please. Okay, one of the most amazing things about cars in the past 50 years has been this incredible revolution in safety. Okay, I'll give you an example. In the mid 1930s, my great grandmother was killed in a car accident where her car was traveling about 20 to 25 miles an hour. It was a fatal car accident in the 1930s. Okay, a few years ago, I was in a car accident where I was going about 45 miles an hour, hit another car that was traveling towards me, and everybody walked away from it. So how do you do that? Well, it turns out the way you do that is you make the car accident last longer, okay? Which sounds really weird, but is absolutely true. So we've got two cars in our test here, okay? They both have the same mass, and they're both moving into a solid concrete wall at 75 miles an hour, which is about 34 meters per second. The first car is equipped with a crumple zone that absorbs the impact over a period of 0.02 seconds. The second car does not have a crumple zone and absorbs the impact over 0.003 seconds. Find the average force acting on each car during the impact. So let's work through this thing, and you're welcome to work along with me as I do this. Let me come over here. There we go. Okay, so what we're saying here is we've got two cars, right? We've got car number one is going to run into a brick wall or concrete wall, right? So here's number one, right? Here's number two. Same thing. Car, wall. Okay, this wall is floating in the air apparently. Okay, so they're both going to hit the same wall, right? But this car, when it hits the wall, is going to crumple, right? Which means that this whole part of the car is just going to smash like an accordion, right? Which means that this car is going to look like it was completely demolished during this collision. This car is, so this is what modern cars do. Cars today, and by today I mean pretty much anything designed in the past 25, 30 years, is like this car, where when it hits the wall, the duration of that collision is fairly long. Now, 0.02 seconds doesn't seem very long, but remember we looked at, you remember when we talked about the bouncing ball, right? Like a tennis ball bouncing off the ground, that whole collision takes less than 20 milliseconds, which is what we're talking about here, okay? So there's our duration of the first collision. Here's our duration of the second collision, right? This is typical of cars built before about the mid-80s. Instead of trying to collapse, they've designed the cars to be as strong structurally as possible, which meant that when you hit something, your car didn't smash like a pancake. Your car tried to retain its shape, which means that these collisions lasted very little time, right? Because there wasn't a whole bunch of smashing and crunching to happen. It was just kind of bang. Okay, so they both have the same velocities, right? They both have the same mass. So they both have a mass of 1,600 kilograms, and they both have velocities initially of 34 meters per second. And they both hit walls, so we know their final velocities, right? After they each hit the wall, their final velocities have to be 0 meters per second, okay? Okay, so let's work this out. Let's figure out how much force was applied. We know that the change in momentum, so our momentum final minus our momentum initial, has got to be equal to the integral of our force, put arrows on all these things, over time. Okay, so for a real car hitting a wall, the force over time is going to be a mess, okay? We'll actually do a video experiment, not today, but next week, that looks at how the force varies for two objects hitting each other as a function of time. It's a mess, okay? It's going to be all over the place, up, down, right? Increasing, decreasing. But the thing is, what I asked for is the average force. So the average force is the force that equals the result of the integral times the time duration, right? So if I come back here and I plug stuff in, right? Okay, my final momentum is 0 because my final velocity is 0. My initial momentum here is just the mass of the car times V initial, and that's going to be equal to my average force times the duration of the impact, right? And if I solve this thing, I get that my average force, oh, by the way, these are still vectors, right? So that my average force is just negative my initial momentum divided by the duration of the impact, okay? And this is the same thing is true over here, right? I'm going to do exactly the same procedure with just swapping out the other time. So the average force over here is just going to be the same formula, but with T2 there. Okay, so let's figure out what this thing is. I can go over, luckily I happen to know you're all at computers or phones, which by the way are also computers. So I can plug in the numbers. I can say 1,600 kilograms times 34 meters a second divided by 0.02 seconds gives me an average force on the car over here of negative 2,720,000. Let's see, do I have enough zeros there? Nope. Newtons. Okay. That's a huge force, but remember, that's the force acting on the whole car. Okay. If I come over here, my average force is going to be the same thing, but divided by 0.03, which means I get negative 18 million newtons. So that's going to be 3, and then we'll round down. Okay. Or in other words, that is negative 2.72 meganewtons. Okay. Mega is a million, right? And this guy is going to be negative 18.13 meganewtons. So which car would you rather be in? Well, obviously you'd rather be in this one, right? Because the force and hence the acceleration that the car experiences is almost a factor of 10 less. And that's really important if you happen to be in this car, because you'd really like to not get accelerated super fast, right? If you get accelerated at this rate, well, you might not make it. But if you get accelerated at this rate, you might. So we can actually figure out what the acceleration you'd get is, right? The average acceleration you'd get is just that number divided by the mass of the car, which is 1,700 meters per second squared, which is a lot, right? That's 170 Gs. It's not something you want to do regularly, but it's survivable for a very, very short period of time. In the other car, you're talking about an average acceleration of 11,300 meters per second squared. That one, you're toast. So this is really, I mean, this is counterintuitive, right? If you tell people, oh, the reason my car accident was safe is because it lasted a long time, that doesn't make any sense from just the way we would approach that every day, right? Of course, we'd want the car accident to be over as fast as possible, except we don't actually. We want the car accident to last as long as possible, because the longer the car accident lasts, the less acceleration and the less force we have to get. So the way you make car accidents safer is by making them last longer, which is why nowadays when cars get in car accidents, it looks like the car exploded, right? It looks like the car just got annihilated. If you see that, it's usually a good sign. Well, okay, good is a strong word, right? But it usually means the car did its job. The car made the car accident last as long as possible so that the people inside of the car were okay, as opposed to a car that just made the car accident last as short as possible. It's probably really bad for the people inside of it. Okay, does that make sense?
Yeah.
All right. How are we feeling?
Good.
Are we fried? We want to do one
Fried.
more? What do you think?
Bit fried.
What do you mean by one more?
That is a wise question. What do I mean by one more? Let's do this one. This one's fairly quick. So let's do this one, and we won't work through it in great detail. Okay, how many of you, okay, first of all, how many of you are willing to admit this? I do this all the time in grocery stores. You get your cart all loaded with food, you get a running start, and you jump on the back of the cart. It's all sorts of fun. Okay. All right. People are willing to admit it. It's great. Don't do it in a crowded supermarket. Actually, nowadays you probably shouldn't do it in any store because everybody's all crazy paranoid and stuff for good reason. But the point is that this is a conservation of momentum problem. So let's suppose you're running, you have some velocity and you jump on a grocery cart full of food, right? We can figure out, based on how fast the person was running beforehand, how fast the person and the cart are moving afterwards. So let me work this out really quick. And we won't even get into numbers. We'll just do this. We'll just work out the solution. So we had initially, we had a person and a grocery cart. There's the handle. Okay. The person had some velocity, right? Some V initial. The grocery cart didn't. And they both have some mass. Here's the mass of the person. Here's the mass of the cart. So if I want to talk about the momentum present here in this system, initially, it's just the initial momentum is just the mass of the person times the initial velocity, the velocity they're running at, okay? All right, now let's talk about after. Afterwards, you have the cart, well, those wheels got really big, and the person who is like hanging on to the cart. Wow, that looks really weird. Okay, you get the idea. So now you have one object. It has some velocity, which I'm going to call V final. And now it has the mass of the two of them together, right? Assuming nothing fell out of the cart. Okay, so our final momentum has to be the combined mass times the final velocity. Now, here's the thing. If I assume that there were no outside forces, right? If nothing else is acting on this, there's no friction, there's no wind, there's no, motor in the wheels, there's none of that. Then that means, because Newton's laws, right? Newton's version of his law says that the sum of the forces equals the change in momentum with respect to time. Well, if there are no forces, that means the momentum can't change, which means that my initial momentum has to equal my final momentum, which means I can solve for the velocity of the cart, right? So this is the same idea as we were doing before, but now we're talking about changing the momentum as opposed to integrating the force. We're looking at this as the change in momentum. Okay, this is
Can you repeat that really quick? Like why? So there's no force?
well, okay, there is force, right? Obviously, she applied a force to the cart applied a force to her, they're holding on to each other. But here's the trick. There was no outside force.
Oh, okay.
There was no force from anything else. And so the total system, right, of the person plus the cart that's momentum had to be constant. Does that make sense?
Yeah.
Okay, so this leads us into our next topic that we're going to go towards, which is this idea that we can use this statement, right? As long as we don't have outside forces, our momentum can't change. Okay? And we'll talk about that more next time. All right, let's stop there for today. And I'll wish you a pleasant weekend. You know, as much as possible, try to get outdoors a little bit. I don't know where you all are, but I'm in Chico and it is lovely today. And it is supposed to rain tomorrow. So I am going to get outside today and do, I don't know what, but I got to get out of this house. So I wish you all a pleasant weekend. Look for, there will be a video experiment posted shortly after class is done. And yeah, stay safe, wash your hands, you know, don't touch anybody. Have a good weekend.